the software that we have provides an engine for the simulation of 2- or 3-dimensional wave phenomena. Right? So the engine point here is important. What that means is we provide the user with a fixed numerical scheme, and we can focus on optimizing that. So we are, in a sense, completely devoid of any physics, and we leave that to the user. The user itself, in the best of all cases, would then just implement a set of partial differential equations and let the engine go on its merry way and solve the equation for us. And one of the examples that I show here is a seismic wave, an earthquake permeating through the Alpine region. And there's one important point about the software is that it's intended to be scalable. So if I show you this little cartoon here, this is a simulation of an earthquake that I can do on my laptop. So fairly few resources, but it comes at the downside that the resolution is not very great. Right, so obviously, if you want to increase your spatial resolution, you want to see more details, you have to go to a bigger machine. And this is the purpose of the software, and this is what we're using Bede for. So quickly, some of the core aspects of our engine is we do have a adaptive mesh that allows us to focus compute at points where the dynamic is strongest. We do so using space-filling curves, Peano curves, hence the name. And we do have a time-stepping mechanism and, of course, load balancing, which allows us to orchestrate our parallelism quite nicely. And then we have a couple of solver schemes. Okay, to talk about the technologies that we apply, the code itself is written in C++. That's the core code. Then we have a thin layer of Python, which allows us to generate application-specific code. And we do shared memory parallelism with OpenMP. We also support CPP threads and Intel's TBB. So shared memory parallelism means you're using the memory within one node and you distribute the compute amongst the compute units in one node of Bede. Then we have our distributed memory parallelism where we use MPI. This is for the communication and the parallelism using more than one node on Bede. And then finally, the cherry on top, so to speak, is the GPU offloading, for which at the time we have chosen to go ahead with OpenMP and CUDA. And so this cartoon at the bottom shows you a scaling test that we've done on Bede, and we had the fortune that we were early users of the system. So we had the machine for ourselves for some time, and we were able to run through a number of permutations of our problem size and how we orchestrate the parallelism. And what we find is that, okay, we're able to use the whole machine, and using more compute resources allows us to reduce the time to solution quite some bit, but not exactly following ideal scaling. And there's also some dependencies on the problem size. So there's more work to be done. But we're on a good way with pure CPU scaling on Bede already. So the final point I want to make is how we do GPU offloading on Bede. So we made a decision, and whether this is a good one or not is not clear, is that we wanted to be vendor agnostic when we were writing the offload code. So we decided not to use CUDA or not to use HIP. So we went with OpenMP, which on paper allows us to be vendor agnostic, and everything should run on all sorts of different GPUs. The good news in this context is that we were able to offload all the compute intensive bits of our code to the GPU, the Nvidia chips on Bede. But it comes with a bit of a caveat. So the many lessons learned in the process in the past few months. So first and foremost, the we started off with the GNU compiler because we were quite familiar with it. The latest one that is also available on Bede. It turns out the offloading with OpenMP is not that well supported, so there's lots of problems with that. So we switched gears and asked for LLVM 11 to be installed after some research in the internet, also with help from Nvidia. And this is more promising, but it's also not extremely straightforward because the capabilities that are working are strictly requiring you to use a certain version of CUDA, in this case 10.1. And there's also annoying things that you wouldn't think were a problem, like linking to libraries. So libraries which have the device compiled code in them, that's simply not supported, right? So, well, it gave us the opportunity to file a compiler bug, at least. That's something. And yeah, so as it turns out, it's not enough to use your existing C++ code and annotate it with these OpenMP pragmas. That just doesn't give you enough speed. So you really have to expose parallelism to the GPU in order to be able to keep it busy. So that's what we're currently focusing our efforts on, increasing the concurrency of our code. Then finally, just a few words about some tools I found useful so other people might avoid some of the mistakes we initially made. So available on the system is a range of Nvidia tools, and we find that the Nvidia profiler that comes with Nsight systems is extremely useful. So it allows you to give you MPI traces, OpenMP traces, and CUDA traces. And you can view that really, really nicely, and you can even annotate your code. You can put instructions in order to get annotations in your profile view. And the last thing that is super useful is called Nsight Compute, and that allows you to profile individual CUDA kernels separately. So you can very much focus on individual compute kernels and hopefully get good GPU utilization eventually. Okay, so that leads me to my incomplete list of acknowledgements. So I have to thank Mark Dixon, was extremely helpful with getting us up to speed with software and whatnot. Then Gonzalo from Nvidia, who's helping us understand why our code is so slow. And then, of course, there's Oleg Rudi who's doing a pop review for our code on Bede at the moment. That's all. Thank you.